Classical mechanics failed to describe how an electron could orbit an atom. An accelerating charge like that of an electron around a nucleus always creates electromagnetic radiation according to Maxwell's classical equation. This means the electron would constantly lose energy and eventually crash into the nucleus. Niels Bohr solved this problem by assuming the electron could exist without radiating energy if they rotated in quantized orbit proportional to Planck's constant. De Broglie later showed that if such quantized orbit exists, then electron must be a waves. Experiments showed that not only electron but all quantum particles like photon and even atom exhibit interference with no exception, implying everything else must be wave too. Erwin Schrödinger developed an equation to explain this wave-like behavior. His equation describes how a wave evolves over time. But the problem is that whenever we detect these quantum objects, we detect them as particles, not as waves. This presents a conundrum. Experiments like double-slit experiments suggested waves, but detection appeared to be indicate particles. So Max Born came up with the idea that we should interpret the wave determined by Schrödinger equation as kind of probability. This allows a single quantum object to be described as wave. So we adopted a wave interpretation of particle which evolves through time according to Schrödinger equation. And analogous to classical wave, it does not have a distinct location. It only has a probability of being found at a particular location. This location can only be determined once we measure it. So now let me explain the core of quantum mechanics. Let me give you an example. If Newtonian mechanics of basketball applied to electron and atom, there would be no problem. Everything would be intuitive and we could relate everything to our everyday experience. But the universe is not so simple. Quantum objects such as electron, photon and atom are not like basketballs. They are like waves because they create interference patterns like we see in double-slit experiment. The Schrödinger equation was developed to explain how these waves evolves, and it's quite accurate. So if we have rigorous mathematical model to describe these waves, what's the big deal since we know how it works? The problem is that we only observe particle or at least particle-like behavior whenever we detect these quantum objects. This phenomenon can be seen in places like cloud chamber and particle accelerators. The subatomic objects seem to behave like particles, not waves. So to incorporate this into our quantum mechanics theory, the concept of measurement was introduced. Measurement means interaction of quantum object with some kind of measuring device, more specifically an irreversible exchange of energy somewhere in the measurement process. But there is a huge problem. No one can explain how and why this is so-called wave collapse occur through measurement. This is called the measurement problem in quantum mechanics, and since all our information comes from measurement of some kind, we can never directly see or touch this quantum world. In classical mechanics, things are concrete and objects have distinct position and velocities. In quantum mechanics, objects have wave-like behavior. They are more specifically described by a wave function, which are abstract mathematical solution to the Schrödinger equation. These waves aren't localized but instead take up all of the space. It isn't until you look for a particle that it becomes what appear to be particle. Before that, the particle is a collection of probability waves that are theoretically extend out to the entire universe. Now this has some consequences. One is called uncertainty principle, which states that you can never know exactly where something is and how fast it is going at the same time. More precisely, we cannot know the position and momentum at the same time. Quantum mechanics work on probability. When we say we can't know where an electron is, it's because of wave. What we mean by wave is wave function from Schrödinger equation, and this related to the probability of finding the electron at any point in space. But a perfect sine wave for electron spread that possibility throughout all the space, so the position of electron is completely uncertain. But a perfect sine wave means we know the wavelength, So we would know its momentum quite precisely because of the Broglie relation where momentum equals Planck's constant over wavelength. So in this case we have infinite uncertainty in position but no uncertainty in momentum. On the other hand, if we want to know the position of electron precisely, we would need to add many waves of different wavelength so that we can get an interference pattern. This localized wave would give us more precise location, but now we have no idea what the momentum is. This is because all the waves that are needed to create the localization, they are of different wavelength and have different momentum using the same de Broglie relation. So either we know the position very precisely or the momentum very precisely, but not the both at the same time. What's important to understand is that this is not limit of our measuring equipments. It's the exact answer to the both momentum and position of quantum object do not exist in the universe at the same time. The universe itself don't know the answer. So you have to ask, why don't we see wave-like behavior in macro objects? Well, big objects like dust particle and other objects do propagate as waves just like electron. In fact, everything moves like a wave, and their wavelength can be calculated just like photon or electron using de Broglie formula. Wavelength equals Planck's constant divided by momentum. But for large objects, the momentum is so bigger than Planck's constant that their wavelength are undetectable fraction of their physical size. So we can never notice their quantum mechanical properties. A second consequence of wave-like behavior is non-locality. A wave exists over multiple regions of space. This non-locality explains interference, but it also means that waves can add together to give a complex interference pattern. So wave of multiple particles can add together to give a single wave function corresponding to multiple particles. This gives rise to strange correlation between such particles. Is a phenomenon called entanglement. We'll explain this in next video. It's a big and most interesting topic in entire quantum physics. The main thing is that universe is quantized. Familiar quantities such as energy, momentum, mass, and even time and space are not continuous. They occur in discrete quantum units. The quantization is not directly observable in our daily experience because the interval between the units are too small for us to notice. So quantum mechanics is all there is. It is everything. Newtonian mechanics or physics of macro scales just happen to be a good approximation of these underlying more fundamental quantum mechanical universe.